Hi, I'm Rajesh, and in this video I'm going to show you how you can follow a happy path to design distributed systems. So let's start. Think like this is the happy path, right? And in general, the happy path for any system is a core flow, right? Or the main work that a system has to achieve, right? So that particular scenario or that particular flow is called the happy path, which is the core idea, right? And if that will succeed, then everything looks good. If so, that flow in general, we can say like a request enters into the system, then system will process it, then commit, and then respond. Okay. So if this is the flow for any system, right, without any exception or dependency or anything else, right, this is the core flow, then we when we want to implement it, right, then we have to set up some of the goals for the success of this flow, right? So goals could be like low latency, right? Request should be completed quickly, right? Minimal coordination. This particular flow will have less dependency on other parts of the system, right? Or external systems or services, right? And then deterministic outcome. So for this, for a specific input, a same output will be generated every time, right? So that is the deterministic outcome. And fourth one is back pressure aware, which means our system should know about the load, right? How much load it can handle, right? And then it should be able to work accordingly. So these are the four goals which we have considered, but it these can be different for your system, right? And how do you decide what all will be your goals? The goals will be the goals the goals will be based on your non-functional requirements or architecturally significant requirement, right? NFR or ASRs, right? So if you don't know much about it, uh, I'm going to start a new software architecture course in which I'm going to explain all these concepts along with many more with real life scenarios and practical implementations. So don't miss it. Now, when we have set up these goals for our system, I'll also take one example so that you will be able to understand it well, right? So for that, we can take an example of e-commerce website. Okay, and here the solution is deployed on cloud, and we are going to take only one flow, which is checkout flow, for this e-commerce website. And checkout flow, you can see like this is the core flow. Checkout means when user is buying a product from the website, right? And that is the core thing. If that works, everything is good. If that doesn't work, then everything will fail, right? And for that, we have one API gateway implemented, right, through which all the requests will uh, pass on to our services, right? So here we have one checkout service, right? And then checkout service is basically dependent on payment service to confirm the payment. And then we have one order DB, which checkout service will update when the order is created, right? and then right. So this is the example, and if you see, this is the main flow. If this flow will work, then our e-commerce site considered successful. If this will fail, then everything is kind of fail. We can say this is the happy path for our e-commerce site, right? So now to achieve these goals, what we have to do, we have to basically set up, or we have to establish some of the thumb rules or principles, right, to basically guide our architecture or the implementation, right. So how do we do that? We'll set up some of those principles based on these goals, right. So first principle, um, we can say like single writer per aggregate, right. Let's understand what this principle is. So single writer per aggregate means a cluster of entities or value objects, right. For example, here we have this order DB, right. So this order DB will have all the order related entities in this database, right. And only single writer means only one service or one component should be writing to this database, right. Like here, only checkout service will write to the order database, right. And why we need this, right? Because if multiple services are allowed to write to this database, then we will have many issues, right, in terms of how the data will be updated, right. And we might have some issues in the data consistency or the making the consensus, right, across services, and different other types of issues, and we might need the distributed transaction pattern to be implemented, right. So many complexities will come into picture, and because of that we might have errors or faults in our system, right. So to avoid all that, we have to establish this one principle so that we can keep this flow simple and effective, right. Now let's see the next principle, which is idempotent commands. So what this is, idempotent commands means if user retries or the same request comes multiple times to the system, right. So retries will not cause any issues, right, or duplicate request will not result in duplicate orders, right. So that is idempotent commands. The next one is thin sync edges and thick async core, right. What this is, this means like the edges or the main functionality or the initial flow that we will be executing, right, for any user request, right, that should be thin and sync. Sync means synchronous, right. So if you see here the checkout, in case of checkout, this flow is about creating order, so this should be thin and it should be synchronous. It should not be like we should put here some events or decouple this communication and this will happen over time, right. We will not be able to track within the same call flow, right. So this should be thin so that this will be easily completed and will get the response quickly, and we will be able to meet low latency requirements, right, or high performance need, right. And we can also address the minimal coordination for this, right. And thick async core means rest of the aspect which are needed for this flow, right, those will be asynchronous, right, those will not be part of this synchronous flow, right. And how we will implement that, those will be implemented for example using a event driven approach, right, or using messaging middleware, right. So Here in this example, what we are saying, when checkout complete, right, order is created, then that update we send to this central pub sub system as an event, right, and all the services uh, subscribe to this event will get an update, right, or will be notified, right, and then they will take the action. Like for example, notification service might send SMS or email notification about the order is completed, right, and then dispatch service will create a dispatch request, right, and inventory service will update the inventory, right. So all these things will be done in async way, right, not part of the main flow. So this principle we have to set up so that this will be implemented to make the happy path thin and synchronous, right. Now the next one, the next principle is bounded request. So what else we have to do? We also have to ensure like our system will have some kind of timeout implemented for all the requests. So if a request is not completed within 1 second, then either we fail that request or we fall back to secondary source, right, to get the data or complete the operation, right. And why we should do that? So that if one service is slow, right, because of that our user experience will not be impacted. In place of getting the response within 2 seconds, it user will get response in 5 seconds or 10 seconds, then it will not be good, right. So that is one thing. Second thing, if our system is able to process 100 requests within a second, right, but one service is taking more time, then because of that more requests will pile up, and then it will impact the ability of our system to process the number of requests, and then entire system's performance will be impacted. And not only performance, if this issue is there for high load system, right, then this can bring the system down, because so many requests will pile up, and then our system will be experiencing heavy load and less performance, and then all the services will heavily loaded with more number of requests, because we are not able to process requests. So in place of 100 requests per second, suppose it will go down to 20 requests per second. Then first second we process 20 requests, and next second when we should be processing 100 requests, now we have to process 180 requests, and third second we have to process 200 uh, and 60 requests, because every second now we are processing only 20 requests because of that slow service or slow dependency, right. So it will impact our system and can bring the system down after some time. So we should have this bounded request principle set up, so that if a particular service is not responded within that period, then timeout occurs, and then either we fail that request or get the data from the secondary source, right. And that way we can not only improve or maintain the user experience, but also uh, keep our system stable, right. So that is the fourth one. As of now, these four principles I am suggesting, but there could be more based on the scenario and complexity of the system, right. So now we have basically set up these principles and designed our system accordingly. Now we have to basically protect our system, right, from fault and errors, right, or issues which can bring our system down, right, or our system will have issues, right. So how do we ensure like our system or our happy path is protected, right? We have to add some of the shields to protect it, right. So first one is admission control, right. So admission control means from the entry point, right, from where the user is entering into the system or raising the request, right, that moment itself we have to control whether a request should be created or not, right. So for example, if payment service is not working, and that is the hard dependency without which order will not be created, right, or checkout will not be completed, right, then in place of stopping here and raising error to the user, right, what we will do, we will disable the checkout feature for time being, right, when this payment service is not working, and we can show some notification to user that we are experiencing some issue with payment confirmation, so please try after some time, right. So that way we will not only avoid showing errors, but also we will protect our system from the load which will not have any positive impact on our system, right. Now what is the second shield? Second shield is circuit breaker. Okay, this is another pattern which we can implement or we should implement to protect our system or happy path, right. And how do we implement? So one place is payment service, right. We have a dependency on payment service, and if we are saying like our checkout flow has hard dependency on payment, and it will not complete if payment service is not available, right, because we need payment confirmation here. When request will come, then we should not be calling payment, right, because we already know the payment service is not working, and that way we will be able to avoid like extra load on the payment service which is already struggling with issues, right. Checkout service will not perform multiple retries, right, and it will be able to return quickly, right. And how we can do that? We can do that using this circuit breaker pattern, right. So what circuit breaker pattern will do, it basically return the error response from here itself. It will not pass the call or request to payment service because it already knows that payment service is not working, right. So it returns the response as error response, right. So we can save some time as well as we can reduce load, extra load on payment service, which will result in error anyway, right. And once payment service start working, then this circuit breaker will close the circuit, and then our request from checkout to payment will work again, right. So this is the circuit breaker pattern implementation where we want to fail fast, right, and avoid calling a service which is not working, and protect our system from extra load or extra time we will put in this call, which anyway is going to fail, right. So second way is, think like checkout service has to check the inventory before completing this checkout flow, right. But suppose inventory service is not working, right. So what we will do, we will return the inventory status for that particular product, right, from cache, and we can say this particular information is 5 minute old or 10 minute old, right. In place of returning the error response from here, we can implement circuit breaker pattern, and we can use a secondary source to basically return information which is not up to date, but it can serve the purpose, right. and we can mention like inventory confirmation is pending, right? So this is another way to implement the circuit breaker pattern to basically protect our system, right? Otherwise the checkout service will fail, right? Because inventory will return the error response. But in this case, it will not return the error response. Circuit breaker pattern will fall back to secondary source and return the response, right? Now let's see the next shield, which is load shedding, right? Load shedding means when we are getting more request or more load which we know like our system will not be able to handle, right? Then we drop those requests or reject those requests. So that is called load shedding, right? And that is another pattern to protect our system with the load which we know like our system is not going to handle, right? And it can bring our system down completely, right? Or can impact the performance of our system, right? So this is another shield. And how we can implement it? We can have like patterns implemented like rate limiting, right? Or throttling, or there are few other ways by which we can do, right? And how we can implement it, I have explained in detail in my video top 5 load pattern, specifically in part 2, where I explained the 2 heavy load pattern and how we should handle in our system. So you can watch that video to understand this particular pattern as well as many other aspects which are very much important for heavy load systems. Okay. Now the next one is graceful degradation. Okay. And graceful degradation means like when something is not working, right? uh, and our entire system will not work or that particular feature will not work. What we can do, we can degrade the functionality, right? And will make a kind of compromise to show something which is not the 100% but at least 50 or 60% of serving the purpose, right? So the one example of this is think like we have recommendation service, right? So when user will log in our system will show recommendation based on user preference, right? To buy the product, right? But think like this recommendation service is not working, then what we can do, we can pull the information based on recently viewed product or top sellers and return to the user, right? It may not be 100% based on the preferences or based on the preference of user, but it will serve the purpose, right? And this is what is called graceful degradation, right? Here bounded request principle we should also implement, right? Where this recommendation service should respond in 1 second, right? But if not, then we pull the data from this cache and show it to the user, right? So we assign a budget to each of the service, for example 1 second for this, 2 seconds for checkout, right? Like that. And if that particular service or that particular primary flow, right, will not work, so primary flow will not work within that budget, right, or will not respond within that budget, then we go to the secondary source and complete the request, right? So this way we will be able to serve and protect our system from the error near service or services which are basically facing issues, right? So this particular method is called graceful degradation, right? So by doing this, we will be able to create a happy path which will survive many issues, and we will be able to keep this happy path working in most of the uh, error scenarios, right, or exception scenarios, right, and we can keep the dependencies minimal. So this is one of the way to design a system by following happy path. So that's all for today. Thanks for watching. Please like and subscribe. Bye.